Hi everyone, this is Dr. Orkun Bajik and I will be talking about the binomial distribution today. I will walk you through a numerical example and we will see how we can solve a binomial distribution problem using Excel functions. So in a binomial distribution, we have a Bernoulli trial. So in a Bernoulli trial, we have three conditions that have to be met. And these conditions are, each trial has two possible outcomes. And those outcomes are the success and failure. So in our trial, we need to have only success or failure. The probability of success, which we denote by P, doesn't change from one trial to another. So we can have multiple trials and the probability of success is the same in every single trial. And the last condition is that these trials are statistically independent, which means that one trial doesn't affect another. A typical example of a Bernoulli trial is tossing a coin experiment. When you toss a coin, you have two possible outcomes, right? So this is the first condition here. So the outcome is either heads or tails, right? So I satisfy the first condition. I don't have a third outcome. Then you are going to define one of these outcomes as success. So in an experiment, it doesn't necessarily need to be a success or failure. It's just a matter of defining this outcome as a success. So heads or tails, one of these can be defined as success and the other one will become failure. So for example, let's say that the outcome being tails is success and therefore the outcome being heads will be failure. So the probability of success in this case is going to be 0.5, right? Because we have 50% chance of heads and 50% chance of tails. So since the success is tails, the probability of success is 0.5. And it doesn't change from one trial to another. You can toss this coin multiple times. Each time the probability of tails is 0.5. So we satisfy the second condition. And the third condition is that the trials are independent, which means that when you toss this coin multiple times, each experiment is independent of each other. So they don't affect one another, which means that they are statistically independent. So in a binomial distribution, our main purpose is to find the probability of a certain number of successes in our experiment. If the random variable is the number of successes in a series of Bernoulli trials, then we call this random variable a binomial random variable. So we need to have a Bernoulli trial and we are looking at the number of successes and then you have a binomial random variable. We are going to talk about two different inputs to a binomial distribution, which are n and p. N is the number of trials and P is the probability of success. So we are going to illustrate this by using a numerical example. So I have an example problem here. Consider the example of students applying for colleges. So we have students that apply for colleges. The outcome of an application is that the student is either accepted or rejected, right? So we only have two possibilities. It's either accept or reject. Based on past data, we know that 80% of the students are accepted. So out of these applications, 80% is the probability that the application will be accepted. So first of all, part A is asking what is the probability that among the next 20 applicants, exactly 16 will be accepted. So we need to identify if this is a binomial distribution. In other words, do we have a Bernoulli trial in this experiment? So we have three conditions and let's check if we meet those conditions. How many outcomes do I have? I have two outcomes, right? Either accept or reject. So this satisfies the first condition. So if we go back to our slides, it satisfies this first condition. The probability of success. Let's define success as being accepted, and therefore being rejected is failure. What is the probability of success? If you go back to the question, the probability of success is 80%, in other words, 0.8. And it doesn't change from one application to another, it's always 0.8. So we satisfy this second condition as well. And the trials are independent. The applications don't affect one another, so they are statistically independent. We satisfy all these three conditions, which means that we have a Bernoulli trial. And in part A, we are looking at the probability of a certain number of successes, which is exactly 16 in this case, out of the 20 next applications. So this is a binomial distribution question. The question doesn't necessarily need to tell you that this is a binomial distribution, so you may need to identify it yourself if you are looking at a binomial distribution question. So in our case, we are in a binomial distribution question. So I will create a template here, and then I will solve this question by using my template and my Excel functions. So I have some values that I know from my question statement. So I'm going to list N, which is the number of trials, P, which is the probability of success, and K is the number of successes that I am interested in. So N is the number of trials, and part A says that among the next 20 applicants. This tells me that the number of overall trials is 20. So N is equal to 20. The probability of success, which is denoted by P, is given in the question 80%. So I can just type 0.8. And in part A, I'm interested in exactly 16 successes. So K, the number of successes, is 16. So I can write question part A mathematically in this form. So probability X equals 16 is how I can represent question part A mathematically. So Excel has a nice function to calculate this probability for us. And that function is binom.dist. And you will need to type 4 different inputs into this function. And the first one is number underscore S, which is the number of successes. So the number of successes that we are interested in part A is 16, so I'm going to select C16. Second, I'm going to enter the number of trials. So this trials part here in the function is asking us how many trials we have. And we know from the problem that we have 20 trials, so we select C14. The third input is the probability of success, so probability underscore S. And I know it from my question that it is 0.8. And the final part is where usually the students get confused. So this cumulative question has two answers, two possible answers. One is true, the other is false. So you are going to decide if your probability question is a cumulative probability question or not. So let's read the question statement one more time. What is the probability that among the next 20 applicants, exactly 16 will be accepted? So it is saying that we are looking at exactly 16. If it were cumulative, it would include a value and the ones below that value. So it would be something like up to and including this value, at most this value. If it says exactly a certain value, in our case exactly 16, that is not cumulative. Therefore, we are going to answer that question as false. Okay? So it says exactly 16, and exactly here is the keyword, or it could simply say, what is the probability that among the next 20 applicants, 16 of them will be accepted? That would also mean that we are looking at exactly 16, which is not cumulative, so we answer that question as false, and the probability is 0.218. So part B, what is the probability that among the next 20 applicants, at most 16 will be accepted? So this is a cumulative probability question because it includes 16, 15, 14, 13, and so on. So all of those possible outcomes up to and including 16 are included in this question. So this is a cumulative probability question, and the notation will be x less than or equal to 16 because it says at most 16 and it includes 16 as well. So we are going to use our function binom.dist. Again, number of successes is 16 in our case in part B. Number of trials is 20. The probability of success is 0.8. And in this case, my answer will be true because, again, it says at most 16, which includes 16 and all the possible values below 16. So the probability is 0.588. And part C, what is the probability that among the next 20 applicants, at least 17 will be accepted? So let's look at this slide over here. So what I have is I have all of these possible outcomes that I can observe within this problem, right? So I have 20 applicants and I might have 0 accepted, 1 accepted, 2 accepted, and so on. And the maximum is that we can have 20 applicants being accepted, right? Because we have 20 applications and it can be none of them will be accepted or all of them will be accepted or anything in between, right? So I have all these possible outcomes. So in the second question, the answer was this red section, right? So in this section, we included at most 16. That includes 0 of them will be accepted, 1 of them, and all the way up to 16 of them will be accepted. So I know that probability. And from the basic rule of probability, I know that the sum of the probabilities of all possible outcomes will have to be equal to 1. Therefore, the sum of the probabilities of these outcomes that I listed here, all of them, will sum to 1. So if the overall sum is 1, and I know this red part's probability, what is the probability of this blue part? That is the question in part C, okay? So again, the overall sum is 1, and I know the probability of the red part. That means this probability in blue will be equal to 1 minus the probability of x less than or equal to 16. All I need to do is to find at least 17, all I need to do is to subtract my probability from 1. So again, in part B, I calculated the probability of at most 16, and I need to find the probability of 17, 18, 19, and 20. Their sum is what I'm looking for. And if the overall sum is 1 by the rule of probability, when I subtract the answer from part B from 1, I am getting the answer for at least 17. So that is my answer. Part D, what is the expected number of accepted applicants? So in binomial distribution, there is a formula to calculate the expected value or the mean. That will be n times p. Do I know n? Yes, I do. That is equal to 20. Do I know p? Yes, it is 0.8. And the answer is 16, which means that the expected number of accepted applicants among the 20 applications is 16. So this will summarize and conclude the discussion about binomial distribution. So thank you so much for watching, and I will see you in the next one.